So in example 1, we saw that we could think about the end behavior and use a table of values to get a sketch of the graph. In this one, again, we can think about the end behavior. We know that it's an x cubed graph. And so it's odd. It's going to act like a line. And because the number in front of x cubed is positive, it's going to act like a line with a positive slope. But in this one, we're going to just look at the x-intercepts and use our skills in factoring to draw the sketch of the graph. So from here, this one is actually a really easy one to factor because there's a common factor. We don't have to use our synthetic division or anything like we did in the factoring before because there's a common factor of x, and once you pull that x out, we're just left with a quadratic, and that quadratic is fairly straightforward to factor. From this, if we set this equal to 0 to find our x-intercepts, we would know that x is equal to 0, -3, and x is equal to 2 are our x-intercepts. So when we go to graph this, and I go on my scale here and I go by ones, I'm going to have an x-intercept here at -3, at 0, and at 2. And from this, we can draw a sketch. This sketch that we're going to draw just says, well, if those are my x-intercepts, and it acts like a line with a positive slope, with my end behavior, I know I'm going to be starting down here. I'm going to have to go through this point, loop through, back through this point, loop through, and back through this point again. And if we draw a smooth curve through each of them, we get an idea of that graph. And this would be enough for a sketch of this graph. If you wanted to be more accurate, you could use the table of values like we did in example 1. What might be some values that I would like to add to this one? Maybe I want to find out how far down it goes at 1. So if I plug in 1, what do I get? 1 times 4 times -1 is -4. So I could plug in 1 and find out that it's -4. I could plug in -1 and -2 and find out some of those values in there. But for what I have right now, this is a sketch. And for the most part, when you're asked to sketch the graph, they're going to be just looking for, do you know what the end behavior looks like? Can you find your x-intercepts? And you'll also be asked to draw your y-intercept. But in this case, our y-intercept was exactly the same as our x-intercept because we had the point 0, 0. And then use your end behavior and draw a nice smooth curve through all of them. And this would be enough. Now, what we don't know is I could have drawn the same thing through those points like the purple one. And we don't know which one's more accurate, the green or the purple. But we are just getting a sketch and getting the basic idea. Again, we have our table of values if we wanted to be more accurate. And we could use our graphing calculator to find out exactly what that local maximum is right there. But for right now and for a sketch, this is all that we're going to need. Now, I'm going to give you your questions for this one, 7 and 13. But before we look at those, we're also going to look at the example right beside it. You won't have to write anything down for this one. Example 3, no, here we go, example 2. We're going to look at this one. So here is one that can't be factored easily. You would have to look at that last number of -6 and figure out something that makes it equal to 0. Apparently, according to the solution there is right beside you, if you plugged in -1 and worked through the whole thing, no, if you plugged in 1, sorry, +1, you'd get 2 minus 1 minus 14 plus 19 minus 6. It equals to 0. That tells us that x minus 1 is a factor. And just like we did this morning when we factored things fully, you could then go to your synthetic division, 2, -1, -14, 19, -6, and put a 1 out in front. Bring the 2 down. 2 times 1 is 2, add. 1 times 1 is 1, add. -13, add. 6. Perfect, we get a remainder of 0. So this tells us that our function f of x, and for writing the division statement, these questions are really nice if you have your original polynomial labeled as a function, f of x, because now I can write my division statement, and instead of writing 2x to the 4 minus x cubed and all of that, I can just write f of x equals x minus 1 multiplied by 2x cubed plus x squared minus 13x plus 6. Now, sometimes for notation, you could just say, I'm going to call this g of x, that little part there, just so that for notation, I can figure things out. I think in your textbook beside they said p of x. It doesn't matter what letter you decide to use. And then apparently, if you plug in 2 in for x, you get 0. So that tells us that x minus 2 is a factor. And if we set up our synthetic division with this new one, 2, 1, -13, and 6, with a 2 out in front, bring down the 2. 2 times 2 is 4, add. 2 times 5 is 10, add. 2 times -3 is -6. Perfect. It works out. So now I could write an updated division statement. I have my original function, f of x. I found out at first that x minus 1 was a factor, and now I find out that x minus 2 is a factor, leaving me with 2x squared plus 5x minus 3. If I factor this now completely, this has to be 2x and x. 3 and 1, I need a +3 and a -1 to make a +5 in the middle. And this is factored completely. Now that this is factored completely, if we made this equal to 0, we would find out that the following are the x-intercepts. And when we go to do a sketch of this graph, we would have 1, 2, 1/2, and -3 as our x-intercepts. If we think about our original function, look at its equation right at the beginning. If you wanted to find your y-intercept, you'd plug in 0 for x. Can you see that your y-intercept is going to be at -6? We know the end behavior of this one because it was an x to the 4 graph with a positive leading coefficient. It's going to act like a parabola that opens up. So as far as our starting point to draw this, we know that we've got to start from up here. You go through, smooth curve, through all of your x-intercepts and y-intercepts, and that'll be the graph of this function. Now, how far down it goes or how far up it goes, you can't tell that from this technique. And you're not expected to figure that out from this technique. This would be enough to draw the sketch. And if another person went way further down than you did, they would get the full marks as well. As long as it's going through each of your x-intercepts and has the correct end behavior, that's all we're looking for right now as a sketch. Again, like I said earlier, if you'd go on to study calculus, then you're going to learn how to find your local mins and your local maxes exactly. But for right now, we're just concerned about getting the right kind of shape and going through all of our x-intercepts and y-intercepts.